thank the organizers for inviting me, and thank you for their hard work behind the scenes, without which this meeting would not be possible. And also thank everyone for being here to my talk. So today I'll present you some work I did on the Norton algebras of distance regular graphs. And I learned this topic from Paul a few years ago. I also want to thank him here. So let me begin with some basics. I think is kind of familiar to many in the audience. So let's begin with a distance regular graph, gamma, okay, with a vertex at x. And the requirement here is for any triple of integers I, j, k, non-negative. We pick any pair of vertices x and y at distance k from each other, and the number of vertices with distance I and j from x and y, that number is called pijk, and that doesn't depend on the choice of x and y. That's called the intersection number. And such a graph is called a distance regular graph, and the diameter is the maximum distance between any pair of vertices in this graph. Let's call this little d. And we know the adjacent matrix of this graph has eigenvalues theta 0 to theta d, ordered decreasingly. And also each of them has the same algebraic and geometric multiplicity. That means the matrix is diagonalizable. And so let's take a look at the vector space R to the x. You can think about this as the space of all the functions from x to r, or you can think about this as the space of all the vectors with components indexed by x, either way. And that becomes a direct sum of the eigenspaces. Let's call them V naught through Vd of the adjacent matrix of this distance regular graph. And of course, there's a lot of nice properties about the eigenvalues and eigenspaces of a distance regular graph. And you can find these properties in any standard reference on distance regular graphs. Okay, any questions so far? Okay, so let's look at an example, the Hamming graph, H and E. So we have the vertex at x consisting of all the words of length n, where each digit is chosen from 0 through e minus 1. So e different choices for each digit. And the H sets consists of all the unordered pairs where each vertex in that pair differs in only one position, exactly one position. So this is an example when e equals 2, so only 0 and 1 for each digit. So when this happens, the graph is called a hypercube. It's well known. We call that Qn, and my graph here is Q4. Okay. So it has 16 vertices. All the length 4 binary strings are here as vertices, and then you connect 2 of them if they differ in one position. And we can also see that when you have 2 vertices with I different positions, that means they are at distance I from each other in the Hamming graph. So this implies that this graph is a distance regular graph with diameter d equals n. And we can also compute its eigenvalues and the multiplicity of each eigenvalue. And you can also use the parameters we have here to express these things. And also, we know the automorphism group of this graph is a Riff product of 2 symmetric groups, SE and SN. SE acts on the vertices by permuting the digits, the E digits, in those words, and SN permutes the n positions in those words. All right, next we're going to talk about Norton algebra. So we look at the orthogonal projection pi I from the vector space R to the x down to a eigenspace Vi. So remember, R to the x is a direct sum of the different eigenspaces. So we can do a orthogonal projection to a particular one. And then this allows us to define the Norton products. We use the entrywise product first. We just multiply 2 vectors from R to the x entrywise. Okay. If you think about them as functions, you just multiply those 2 functions. Or if you think about them as vectors, do the entrywise product. And then we take 2 eigenvectors from one eigenspace and do this entrywise product. You may or may not get a result in the same eigenspace, but you can do the orthogonal projection back to that eigenspace. And that's the Norton product. And with this product, the each eigenspace becomes an algebra, and that's the Norton algebra. Vi with the product star here is commutative, but it's not necessarily associative. Okay, so this Norton algebra has interesting properties. For example, is automorphism group is kind of interesting. So it was studied back in the 50s or 60s by the group theorists because they are interested in they were interested in the automorphism groups, and I believe is related to even the construction of the monster simple group. But let me not talk too much about that here. And we're going to look at the Norton algebras of certain distance regular graphs, not only studying the automorphism group of this Norton algebra, but also I want to study them from sort of a combinatorial perspective. So I'm interested in this Norton products being non-associative. I want to measure the non-associativity of that. And I'll be precise in a minute. Okay. So that's the two goals in my work. So let's talk about the non-associativity of a binary operation. So let's start with a binary operation defined on a set X. And you can look at some indeterminates, x0 through xn, taking values from the set X. And then you can form this expression, x0 star x1 star dot 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 star xn. And of course, you need to specify an order, right? Without parentheses, our convention usually is just from left to right. But if you want to do it in a particular way, you'd better insert parentheses, unless your operation is associative, like addition. If it's not associative, we need to insert parentheses, and the number of ways to insert parentheses is the well-known Catalan number. Okay, when you have x0 through xn, n-1 indeterminates, then you have Cn many ways to insert parentheses. Okay, Cn is 1 over n plus 1 times the binomial coefficient 2 and choose n. Okay, and I list the first several entries of this Catalan sequence. So let's look at some examples where the operation is not associative. So the first example I thought of is minus. No, instead of plus, let's do minus. So you see we have 5 different ways to insert parentheses when you do x0 minus x1 minus x2 minus x4. Okay, so we all know that, but then I thought about this a little more. So let's just expand all these different ways of his parenthesization. And I got actually only 4 different results because my operation is a very specific one, is the minus operation. Okay, you can see those 2 red ones are actually identical. So what does this mean? Well, that means you can actually get an equivalence relation when you parenthesize all the expressions x0 star x1 star dot 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 star xn. There's Cn different ways to do that, but some of them may be equivalents in the sense that they give you exactly the same function from x to the n plus 1 to x. And we're going to denote, let the C star n denotes the number of equivalence classes, okay, for these parenthesizations. And C tilde star n is going to be the size of the largest one. And back to my example of the subtraction operation, we have 5 parenthesizations here. Well, n is 3. And there's only 4 equivalence classes because those 2 red are equivalent. Then those 2 red gives you the largest equivalence class. So C tilde would be 2. Is the definition clear? In general, you can see that C star n is always between 1 and the Catalan number Cn, and same with the C tilde star n. And when you have an associative operation star, then C star n and C tilde star n are both 1, right? It's kind of, oh no, C tilde star n is going to be Cn. C star n is going to be 1. In general, these 2 numbers would vary between 1 and Cn. So I thought that this would be something interesting. We can use this as a quantitative measurement for the non-associativity of this operation. And later, I'll talk about the Norton algebras and see how they are non-associative in this sense. But let me talk about a little bit background here. So there's actually some work on the first number C star n that I just defined. 2 independent works, one by Sakani and Waterhauser, and they call C star n the associative spectrum of this operation star. And then independently, Breit and Silberger also studied that, and then they call that the sub-associativity type. Okay, and we were not aware of these work, and then we just came up with that notion ourselves, together with C tilde star n, and we didn't have a name, so there's no conflict of name. I mean, they had one, but they had some conflicts, but I don't have one with them. So we just didn't have a name. We first studied just plus and minus pretty elementary, and then later we thought about a one parameter family of operations generalizing as plus and minus. And later on, we came up with an even larger 4-parameter family of operations, generalizing all the previous ones in our joint work with Nick Hine. And we used roots of unities and also elements like nilpotent elements and stuff, and using a polynomial ring with 2 independent variables, making some quotients and stuff. And I should also say that if you look at the generating function of C star n, it actually turns out to be the Hilbert series of the non-symmetric operad associated with this operation star. So there's this operad theory for binary operations, and there's some connections there too. And we will call the other extreme case when C star n is Cn, the Cathode number Cn, we call that totally non-associative. So that's the other extreme case. Any question? Okay, let's go. Let's look at another example before I go back to Norton algebras. So after plus minus, we thought about this double minus operation. So A star B is defined as A minus B. So we call that circle minus. So let's just denote C circle n r. Let that be the number of distinct results from parenthesizing the expression x naught, circle minus x1, and so on to xn, with exactly r plus signs. So if you insert parentheses and expand, you're going to get some plus or minus signs right in front of each term. I just count how many are there, and let's fix that number to be r. The number plus, fix that to be r. And then you can just add those numbers as r varies, and I get the total counts for C circle minus n. And with 2 undergraduate students, Mickey and Xu, back in 2017, we find some nice formulas for these numbers. So they are, in some cases, just binomial coefficients. In some other cases, they're not quite, so maybe one less binomial coefficients, or maybe just 0. It depends on some, modularity relation. And I'll show you the table here when n is and r is small. I think it's like a Pascal's triangle, but it's truncated and also modified a little bit. There's that red diagonal. Each entry is 1 less than the corresponding binomial coefficients. And I just add each row. I will get the C O minus n, and then that's not so hard. We get the formula. And it turns out that this last result, the C circle minus n, matches with the sequence in the OEIS. And it's a pretty interesting one. And you see the first several terms, and you may already observe some recurrence relations. So each time you just multiply by 2 or add a 1 even to get the next term. So times 2, and then times 2 plus 1, times 2, and then times 2 plus 1. So you can use this recurrence to generate the whole sequence. And it turns out that there's also more interesting things about the sequence. You can also find the integer with an alternating binary representation of length n, and then turn that integer back to the ordinary number. So you get the corresponding sequence in that, the corresponding number in that sequence. And of course, there's closed formulas, and there's also a game that's called Chinese rings game. Even though I'm originally from Chinese, I didn't know that game. And then I searched that game. I don't know if I can actually do that here. If there's internet, I may be able to. Okay, let's not try that. It should be clickable, but I don't know. Let me go back. Okay, I'll go back. Oh, it's okay. Oh, okay. First one. That's the game, and you can see some like rings attached to some strings or something on a bar, and then you're supposed to try to unattach those things, but you have to follow some steps, otherwise you will get screwed up. Okay, there's videos you can find where people try to like break a record with like a 10 rings or something. You know, how fast they can untangle everything. But it turns out that the smallest number of moves for you to do that when the number is n is actually is the nth number in that sequence. Can you go back to this? Okay, yeah. So now a couple questions I want to ask. So is there a bijection between various objects counted by this sequence? That's a natural question that combinatorists are interested in. Including the one we just find, we don't know any direct bijection with the other objects counted by this sequence. And also we also have that C2 thing for the size of the largest equivalence class. And I computed those first 10 terms or so in this sequence. I have no idea what this is. Now let's go back to the Norton algebras. Let me show you this slide again. So it's about the Hamming graph. This is sort of like a running example for my work on Norton algebras. So let me first present you the my results on the Norton algebra of the Hamming graph H and E. So we look at a eigenspace Vi, and we find a basis for this eigenspace. Let's call that tau sub u, where the u runs through all the vertices with exactly I non-zero entries. So remember, every vertex in the Hamming graph is like a word of length n. I want the non-zero entries to be exactly I. So select those vertices, and each of them is going to label or index a element in the basis of this Norton algebra. And more importantly, we need to know how these basis elements multiply under the Norton products. And we have a formula. So we just add the underlying vertices. We multiply two basis elements. If the sum of those two vertices, they're words, but you can add them components wise. If the result still has I non-zero entries. If that's the case, we just add those two vertices and then take the corresponding basis elements. Otherwise, this Norton product is just zero. And with this formula for the products, we can study the automorphism group of this Norton algebra. When the number E there is at least 3, we find out that this automorphism group of Vi is trivial when I is 0, or isomorphic to the root product of Sn and Se and Sn if I is 1. Remember, that's exactly the automorphism group of the graph H and E. But in other cases, it's not quite like that. We have a root product of S3 and S2 to the n minus 1 when I equals n and E equals 3. And also in other cases, we were not able to determine completely the automorphism group of this Norton algebra. We've got some partial results. We find a subgroup isomorphic to ZE semi-direct product with ZE cross, and then root product with Sn. Okay, and then our other goal, remember, is to determine the nonassociativity using our measurements. So we find out that when I is 0, this product is just associative. So not very interesting. And if I equals 3, no, E equals 3 and I is either 1 or n, then the non-associativity of this Norton algebra is exactly the same as that double minus operation. And we came up with the double minus operation without knowing any connection with the Norton algebra. So it was kind of interesting to see this connection here. And also there's that other extreme case, this Norton algebra could be totally non-associative when E equals 3 and I is strictly between 1 and n, or if E is greater than or equal to 4 and I is between 1 and n. Okay, I'll give you some examples. So H2, 3, so length is 2, and each digit has 3 possibilities, 0, 1, or 2. So we have a basis for, oops, I think oh yes, right. For V1, so I want only one non-zero entry. So of course we just get 0, 1, 0, 2, 1, 0, 2, 0, right? Those are the only vertices with one non-zero entry. And then we made a Cayley table for the products, for the Norton products. And then H2, 3 is kind of similar. And you can see the operation here, like if I pick 1, 1, 2, 1 and multiply, I will get 0, because when you add them, you will get 3, 2, and 3 is 0 mod 1, mod 3. So you only get one non-zero entry instead of 2. So the diagonal entries are those that give you non-zero results. And I should also say that on my previous slide, I didn't really tell you about the non-associativity of the hypercube. That's the Hamming graph when E is 2. I have an example here, and I'll give you the result on the next slide. The example here, when you have the graph H32, which is a hypercube Q3, we look at the Norton algebra, let's say V2, then we have three positions in the words. Each one is either 0 or 1. So that just means that you can select a subset of 1, 2, 3, and then let those entries be 1, the others be 0. So we just call the subset we want to select for the non-zero entries to be RST. And then we have the product this way. And then the bottom line there, if you look at the formula, that actually is something kind of like playing that rock, paper, scissors game. Like RS gives you T, ST gives you R, and stuff like that. So next, let me show you the results for the hypercube. That's a Hamming graph, H and E with E equal to 2. And again, we just have a set S. That's a subset of the positions 1 through n. And they correspond to the non-zero entries of the vertices. So VI is going to have a basis labeled by those subsets with cardinality I. And then when we multiply the two basis elements labeled by S and T, we do the symmetric difference of S and T. And we hope they still have I numbers, I elements. Otherwise, we just say the result is. And we will also determine the automorphism group is trivial in some small cases. And then also it could have could be the general linear group of VI that's pretty big when I is greater than the floor of 2n over 3, or if I is odd, or you can find a subgroup that's isomorphic to the hyperoctahedral group S and B, so it's assigned permutations modulo plus or minus 1. If I is from 1 to n minus 1 and is even. And also for the non-associativity of this Norton products, we determined is also associative when I is 0, I is greater than 2n over 3, or I is odd, but totally non-associative otherwise. So it's often one way or the other, either associative or totally non-associative. But occasionally we see some, intermediate cases like what we showed you about the Hamming graph, H and E when E is greater than or equal to 3, and the double minus operation shows up here. Shows up there, not here, but and actually our method uses something called linear character, and I want to go over that a little bit here. So you can look at a group G, and you look at a homomorphism chi from G to the multiplicative group of C, and this homomorphism is called a linear character, and then you can look at the group of all these linear characters defined by this entrywise products, and that's like the dual group of G. And when G is a abelian group, these two groups are actually isomorphic to each other, and they actually form a basis for the space C to the G. It's not R to the G; we have to allow complex numbers, and then we can look at a abelian group G with the operation expressed additively, and we choose a set S that doesn't include 0 and is closed under taking negative or opposite, and then we can form the Cayley graph, right? That's something familiar to everyone, I believe. So this Cayley graph gamma G S has vertex at G, and then H set consisting of pairs or unordered pairs whose difference is in that set. And it turns out that for this Cayley graph, we can actually find a nice eigenbasis, and those the elements there are actually the linear characters of the underlying group when the group is abelian. And there's of course extensions to the non-abelian cases, but let's focus on the abelian case here. And we can apply this idea to the distance regular graphs. If this turns out to be also a Cayley graph of a abelian group, then we can just find this eigenbasis consisting of the linear characters, and then we can form the Norton products. And it's similar to what I did about the Hamming graph. You just look at two linear characters and you compute the entrywise product of them. And then that entrywise products, you need to find the corresponding eigenvalue, and you just evaluate that entrywise product of the two linear characters at all the elements of S and add all of them. And that's how you compute the corresponding eigenvalue. And if that matches with the eigenvalue of the two linear characters you began with, then you get the right results for the Norton product. If it's not, then you just say the answer is 0. This is actually how we got the results on Hamming graphs. We use linear characters for Cayley graphs of the finite abelian groups. And that means that we can apply this to a bunch of other graphs, not only the Hamming graph. There's the folded cube. Let me not talk about the details. You can form that from the hypercube by doing some extra operations. The half cube or so is another one. There's also the folded half cubes. These are all distance regular graphs. And there are also Cayley graphs of abelian groups. And there's also the bilinear forms graphs. You look at matrices, B times E matrices with entries from a finite field FQ. And two vertices are adjacent to each other if the rank of the difference between them is exactly 1. So it's kind of like a Q analog of the Hamming graph. And this is also the Cayley graph of a finite abelian group. So you can also apply our previous result to this. And there's, of course, more. Okay, question. So now, that gives a question. So what about the Johnson graph, which is a very important example of distance regular graphs? I don't think it is a Cayley graph. It's defined in this way. So you have the vertices being K subsets of a fixed set 1 through n. And then two vertices, if the intersection of them is K minus 1, then they are connected by an edge. And we can compute the distance. If the difference, if the size of the intersection of two vertices is K minus J, then they have distance J from between each other. And then, this is a distance regular graph, and we can assume that n is greater than or equal to 2K, because there's a symmetry when you switch the K to n minus K, you get an isomorphic graph. And we can even compute how many vertices are there at distance R from a given vertex. Diameter is K. Two cases where you can get the complete graph from JN1, JN2 is a line graph KN, okay, familiar examples. And you can compute the eigenvalues and the dimensions of the eigenspaces. Standard results on Johnson graph. And then the Q analog is the Grassman graph, where you take, instead of the subsets, K subsets, you look at K dimensional subspaces of an n-dimensional vector space over FQ, and it will require the intersection of two spaces to have dimension 1 lower to have an edge between. And you can also put some kind of form on this for the spaces, and you get dual polar graphs. Okay, let me not talk about the details too much here, but all these are distance regular graphs. And we have some results on the Norton algebra of these graphs. So there's a previous work by Grassman, Maldonado and Penazzi on the Norton algebra V1 of these graphs. So V1 corresponds to the second largest eigenvalue. And the largest one is kind of trivial, but the second largest one is the next interesting case. And then they got some results, and based on their results on the Norton algebra of V1, we were able to determine the nonassociativity of this product. So I'm kind of running out of time a little bit, so let me be quick. So they introduced some lattice associated with those distance regular graphs, like the Johnson graph and Grassman graph. And then this is a graded lattice, and you can get a filtration from this lattice, and then from that filtration, they were able to get the formula for the Norton products on V1. Okay, so it's kind of complicated. Okay, let me not talk about the details, but this is also valid for the Hamming graph, I should say. Okay, but we've already known the results for Hamming graph, all the Norton algebras of the Hamming graph, so we don't have to go this way. But for Johnson graph, for example, we had to use this formula for the Norton products on V1. And it turns out actually when n is greater than 2k, the Norton algebra V1 of the Johnson graph at j and k is isomorphic to V1 of the Hyman graph H1n. But when n and k is greater than or equal to 2, the Norton algebra V1 of the Grassman graph JQ and k is totally non-associative. And also for the dual polar graph, the Norton algebra V1 is totally non-associative as well, except for just one exceptional case, it's D22. In that case, is the double minus operation again. So again, it's often the extreme cases associative, totally non-associative. But in between, sometimes we see some exception here, and it's equally as non-associative as the double minus operation. Okay, and recently, Paul Terwilliger got a nice formula, or two, or maybe even 3 nice formulas for the Norton algebra, the Norton product on V1 when your graph, distance regular graph is Q polynomial. But what about the Norton algebra VI when I is greater than 1? So you look at the eigenspaces corresponding to the eigenvalues, theta I, not the first one, theta 0, or the second one, theta 1, but the rest of them. What can we say? That's still something we don't know yet. Of course, when you have a Cayley graph, like what I presented earlier today, we have a way to do it, although we need to allow complex numbers, even though the eigenvalues and eigenspaces are all real. Okay, so we have to do this. It's a sort of a mild compromise, I think. And actually, for J and K, the Johnson graph is not Cayley graph, but we know the eigenspaces. We can construct all the eigenspaces of the Johnson graph by either linear algebra or using some representation theory. But I wasn't able to get any results on the Norton algebra, VI when I is greater than 1. So that might be something that somebody can do in the future. I feel like there has to be a way to do it, but I just got kind of confused with the construction of the eigenspaces of the Johnson graph. So I didn't go anywhere from that work. But I should say that, as we explained, often you get totally non-associative or associative Norton algebras, but there's an interesting intermediate case that often show up. And I think that's kind of interesting is the double minus operation. Again, when we introduced that operation, we had no idea this could be connected to anything algebraic. I just thought plus minus, let's just do double minus, right? Is there any explanation for this? I'm not sure. Okay, it's kind of a mystery to us right now. Okay, I'll just stop here. Thank you for listening. Yes.
Have you considered extending VI to, let's say, a sum of eigenspaces, consecutive eigenspaces?
Oh, that's a great idea. I haven't thought about that.
Like if you have a Q polynomial condition and AI star is 0, then the Norton algebra is trivial, right?
Yeah.
AI star is 0. But if AI star is 0, like in the Q bipartite association scheme, then you could take 2 consecutive spaces and project into each one into the opposite one.
That's an interesting idea.
But I mean, for the Johnson scheme, it just seems that you want to build up because of the way the flow set grows.
Yeah.
It seems that you want to work inside consecutive sets of eigenspaces. Paul's got a comment.
If we not plus V1 trivial step into the Q polynomial, that one should be
that one.
interesting.
Yeah.
Just the first 2.
Yeah.
Then the first 3.
Well, it's actually kind of similar to that lattice construction, that gives this filtration.
Yeah.
That's kind of
That's
like that.
That's probably the regular semi-lattice in the sense.
Yeah. But it seems hard to just try to get a particular eigenspace for the Johnson graph. Seems hard to me. It's easier if you work on some consecutive ones.
So an interesting open problem for any given example, such as the Johnson graphs, is to find the idempotence of the Norton algebra. Now, let me clarify what I mean by that. We're not talking about central idempotence, but we are talking about non-zero elements whose stars, square root of the Norton product is equal to the thing itself, or perhaps a scalar multiple of the thing itself. Those things should have combinatorial significance.
I think I had some construction for those idempotents, but for the Hamming graph and stuff, but maybe not for Johnson graph.
Yeah.
So I think I used the idempotents when I studied the automorphism group of the Norton algebras of the Hamming graphs or even Cayley graphs maybe. But for Johnson graph, I don't know.
Okay, yeah, so I just toss it out, be nice paper for any example to work out carefully. What are the idempotents for the Norton algebra?
Yeah, I don't know.
So I mean, the columns of VJ, right? The columns of VJ are going to project back to themselves. Right? If QJJJ is non-zero, right? It'd be others, yeah.
Any other questions? If not, let's thank Jia again.
Thank you.